Hey everybody, I'm here to do a lecture on exponential functions. Specifically, I'm interested in the different forms of exponential functions and how that relates to exponential growth and decay. I hate making videos, to be completely honest, but I couldn't find a video on YouTube that addressed this, so here it is. An exponential function is a function of the form y equals some base whose exponent is x. Okay, that is the parent function, and you can stick any number. Well, we'll look at what happens when you stick different numbers in here. But, of course, function transformations, we could go crazy, right? We could say that y equals, I don't know, some number times this to the, and we can stick stuff in here like some constant times x plus some other constant, and then okay, so what the heck do these do? Well, this is a vertical stretch or compression, or I should say, flip across the x-axis. This would be a horizontal stretch or compression, and or flip across the y-axis. Let's see, this would be a horizontal shift, and this would be a vertical shift. And the order you do it in depends on whether you factor the C out of the D or not. I had another video on that, so I'm not going to get into it now. So these are all the possible transformations you could do to the basic exponential function. And usually what we see when we're talking about exponential growth is we usually see something like y equals a times your base, and then usually a multiple and your x value. Okay, so usually what we see is this. All right, so let's talk about briefly some exponential functions. A really basic one would be y equals 2 to the x. Another one would be y equals 4 to the x, or y equals 7 to the x. And these all have some things in common. So let's look over at desmos.com and graph some of these. Here we are at desmos.com with their fabulous graphing calculator, and I've graphed a whole bunch of integers to the x. You can see that these show characteristic exponential growth. That is, when there's a little bit of your thing, the slope is very shallow. And then as there gets to be more and more, the slope gets steeper and steeper. And you'll notice also they all go through this point here at 0, 1. Okay, so whoops. They all go through the point 0, 1. They have a horizontal asymptote at y equals 0, and they start out shallow and get very steep. That's what exponential functions look like. The cool thing about exponential functions is even if they have a different base, we can still make them look the same by messing with our other variables. So let's say we have y equals 4 to the x. I'm picking, by the way, an example that has a really nice, clean answer. You can do this with any exponentials. It's not going to be as pretty and as clean. And so when we get into exponential growth and decay, we can write these problems many ways, but there's usually one way that's clean and then a couple ways that are kind of ugly. All right, so if we wanted to change the base, so this was, say, 2 to something, we would say y equals, well, I can rewrite 4 as a power of 2. That's why this is so clean. So 2 squared is 4. And so this is 2 squared to the x. And then the power of a power rule says that if I am raising a power to a power, I can just multiply those exponents. So by changing the constant multiple on my x, I can also change the base. It's kind of like it's a balancing act, sort of like 1 plus 4 is the same as 2 plus 3, and we can balance these. We can change the multiple of our x and also change the base. So that comes in really handy, and that's what transforming these the various forms of exponential growth from one to the other has to do with this idea of if you change the base, you also change the constant multiple.